I guess we can get started. Yeah. So good afternoon.
I have 1 minute.
So good afternoon, everybody. It's my great pleasure to introduce Professor Bruce Berndt from the University of Illinois. Professor Bruce Berndt works in the area of analytic number theory, but perhaps a more accurate description is he works in Ramanujan. That is his specialty. And Ramanujan, one of the most enigmatic and romantic figures in the history of mathematics, as you all know. So most people, when they look at formulas of Ramanujan, they get chills. But Professor Bruce Berndt is one of the few people on earth who has the brain power and audacity to actually penetrate through these obscure, wild formulas and shed some light on the work of Ramanujan. And his work has been recognized internationally through numerous awards. I will not have time to list them all, just state a few. So he's received awards from the Mathematical Association of America. He received the Allendorfer Award, the Ford Award from the American Mathematical Society. He received the Steele Prize for Mathematical Exposition. He received the Guggenheim Fellow. And in 2012, he became a Fellow of the American Mathematical Society. And in the same year, he received an honorary doctorate from Shastra University in Kumbakonam, India. Incidentally, Kumbakonam is the hometown of Srinivas Ramanujan. So he's an associate editor for numerous journals, including the Ramanujan Journal. And about 33 students completed PhD under his supervision, and there are more with whom he's been working. He supervised several postdoctoral fellows, and he published quite extensively, 240 publications and 14 books, a lot of them focusing on Ramanujan. So we are all very excited here to have us here because he's going to take us on a very fascinating journey of having lived with Ramanujan for 40 years. So please join me in welcoming Professor Bruce Berndt.
Thank you for the kind introduction. My CV on my website is a bit out of date. I've had 36 PhDs.
Oh.
So this talk will be somewhat autobiographical because I will tell you how I became interested in Ramanujan's work. So the beginning part of my talk should be understandable to everyone because it will be non-mathematical sense. So let me begin with this most famous photograph of Ramanujan. This is his passport photo. There are only 4 photographs of Ramanujan. They all were taken in England. So in this passport photo, which was taken just before he returned to India in 1919, Ramanujan was very ill at that time, and he was too sick to go to the photographers for his picture, so the photographer had to come to the nursing home to take this photograph. And he's actually in his bathrobe here in pajamas in this picture. And this is not really the way he looked for most of his life because he had lost a lot of weight before this photograph was taken, as you will see in the next 2 photographs that I will give. So this is Ramanujan when he became a fellow of the Royal Society. So just 2 weeks ago, there was a meeting at the Royal Society in London where we celebrated the 100th anniversary of his being elected to the Royal Society. So the Royal Society is probably the British analog of the National Academy of Sciences in the US. And you can see here from his countenance that he really was heavier at that time than he was when he went back to India. And this is another picture of him. There's another photograph of him with some friends that was taken at the same time. Again, you can see he's much heavier in this photograph. Well, let me just tell you a little bit about Ramanujan and his work in India. Ramanujan worked on a slate. This was very common in those days in India. And what Ramanujan would do was to do his mathematics on a slate and then record just the final results in notebooks. Paper was very expensive, so to work on paper was just prohibitive. And this is actually the slate on which Ramanujan worked then. And the reason we have this slate is that Ramanujan was hired by the Madras Port Trust Office for 2 years, 1910 to 1912, before he left for England. And the person that hired him was the chief accountant, S. Narayana Iyer. And Ramanujan and S. Narayana Iyer, who was really one of India's best mathematicians at that time, developed a very close association. So if you admire a person and respect the person, you trade slates with them. So when Ramanujan went to England, he traded slates with S. Narayana Iyer, so it's in the Narayana Iyer family now. So unfortunately, this grandson has passed away. It's now in the hands of Narayana Iyer's great-grandson. So Ramanujan then recorded his results in notebooks, and we don't know exactly when he began this. We think it's about 1904 when he entered the Government College of Kumbakonam. He failed his exams after 1 year because he was concentrating only on mathematics. And so he tried once again to get a college education in Madras, or Chennai as it's now named, but the same thing happened. He failed his exams because he concentrated on mathematics. So there are 3 notebooks that exist in addition to the lost notebook, which I'll talk about later. And they're at the University of Madras Library, and I took this photograph many years ago. So some of you in the audience might not know that we used to take pictures with flash bulbs on our camera. So maybe you haven't heard of flash bulbs before. So you can see that my flash was reflecting off of the page here. So why was it reflecting off of this page? Well, what happened was that the library at the University of Madras, where the notebooks were kept, wasn't in the best climatic condition, and insects were destroying the pages, worming their way through pages. So they decided to laminate the pages of the notebooks to prevent further deterioration. Well, in 2012, a new edition of the notebooks was published, and it was discovered at that time that the lamination was not what should have been done because the pages were now cracking and crumbling. So they delaminated all the pages of the notebooks. So here is the new edition. I actually just took this picture on our buffet about a month or so ago. So that's the buffet in our dining room, and we put an Indian tapestry behind it, so we thought that would color the picture a little bit better. Yeah, this new edition is actually much easier to read. They did an excellent job in reproducing the notebooks. So the second notebook is the main one. It's a revised, enlarged edition of the first, but there are lots of things in the first edition that actually are not in the second. A lot of things in the first notebook, not in the second. And the third notebook is actually quite short. Well, after Ramanujan died, B.M. Wilson and G.N. Watson began to edit these notebooks, which were sent to Hardy, I think in 1923. They just sort of made a handwritten copy, and then they were returned then to India. So B.M. Wilson is actually one of the editors of Ramanujan's collected papers, along with Hardy. And this is Watson. So because Wilson died very early, I think he was just 35 when he died, the editing of the notebooks was never completed. So let me tell you a little bit about Watson. He was a professor, I should say professor, of mathematics at the University of Birmingham for many years. See, in those days, there was only one professor of mathematics. That was the title. So some of you wouldn't be professors now in that system. So he was a professor at the University of Birmingham for many years. And when he retired, the new professor of mathematics was Robert Rankin, who was Hardy's last PhD student. And Watson died in 1965, and two people in particular went to visit Mrs. Watson after her husband's death. One was the son of E.T. Whittaker. So some of you, I'm sure, have heard of the book Whittaker and Watson's A Course in Modern Analysis. Of course, it's not modern anymore, but at least then it was modern. But this is one of the classic books in analysis. I've used it all my life. It's a great book. And the other person to visit Mrs. Watson was Rankin. So Rankin actually succeeded Watson as professor of mathematics, but he assumed the position of professor of mathematics at the University of Glasgow when that position opened up. So Rankin was a Scotsman, so that's why he returned to Scotland to become professor of mathematics there. So Rankin and Mrs. Watson then had discussions of what they should do with all these papers that Watson had left in his attic floor office. So they agreed that what should be done is that Rankin would sort through all these papers, and then those worth preserving he would send to Trinity College Library for preservation. So Watson had always been very fond of Trinity College Library, so they thought this was the best thing to do. So during this time, there were papers of Ramanujan in the attic floor office in Watson, including what we now call as the Lost Notebook. And there were other unpublished papers or fragments of Ramanujan as well. So over a period of about 2 or so years, Rankin would then take trips to Birmingham and sort through these papers and send those worth preserving to Trinity College. So here's a photograph of Rankin. So when I got my doctorate at the University of Wisconsin in 1966, I went to Glasgow for 1 year as a postdoc. I wasn't called a postdoc in those days, but anyway, my mentor was Robert Rankin. And one day I was talking with him about Ramanujan in his office. And I had only just barely heard of Ramanujan and didn't really know much about him. And so this would have been during the time in which Rankin was going to Birmingham, sorting through these papers. And I wish I had had a recording of this conversation, because I don't recall that he told me that he sent some papers of Ramanujan to Cambridge. I really regret that. But I do remember that he had a copy of the notebooks. So they were published not until 1957 by the Tata Institute in Bombay. So you know, he described these notebooks for me, and he said, "I'll be glad to loan them to you if you wish." And I told him I wasn't interested. But so then I was hired after 1 year at Glasgow at the University of Illinois by Paul Bateman. He was the head of the department at that time, analytic number theorist. And so in those days we had a head and not a chair. So the head had much more power than a chair does. So anyway, I'm thankful that he hired me. And after a couple years there, he gave me 2 papers that Emil Grosswald to referee. Okay, now suppose I'm being a bit unethical here, because normally a referee doesn't tell others that he refereed certain papers. But anyway, Grosswald has now passed away, and I did accept the papers at any rate. So in these 2 papers, Grosswald proved some formulas in Ramanujan's notebooks, in particular chapter 14 of the second notebook. So I didn't think much about it for a few years, but then my first sabbatical in 73, 74 was at the Institute for Advanced Study in Princeton. And one day in February of 1974, I returned to these papers in Grosswald, and I saw that these results I could prove by using some transformation formulas for what are called generalized Eisenstein series. So I was very excited about that I could prove all these formulas that Grosswald had proved. And although the Institute did not have the Tata Institute's photocopy volumes, Princeton University Library did. So I borrowed these from the library, found a few other formulas I could prove, but a few thousand others that I couldn't prove then. So I went back to Illinois, and of course I tried to get as much out of my theorems as possible. So I didn't head back to, here's the picture of Grosswald, until May of 1977. So when the semester ended, as a challenge to myself, I said, let's try to prove everything in chapter 14 in the second notebook. So I chose this chapter because the formulas that Grosswald and I had proved are from this chapter, so I had a head start on this chapter. So there are 87 formulas or results in this chapter altogether. So let me just tell you about a few of them. So this is one of those from Grosswald's paper in chapter 14. So it's a transformation formula involving the Riemann zeta function. So this is just another version you get by expanding these things in geometric series and collecting powers here in terms of the sums of divisor function. And then on the right side, the B2k, B2n plus 2 minus 2k, these are Bernoulli numbers. Yeah. So it's a transformation formula involving zeta 2n plus 1 that has some similarities with the values of zeta 2n, which are well known. Okay, if you set alpha and beta to be pi, and by the way, this relation alpha beta equals pi squared, Ramanujan loved that kind of formula where you have alpha beta equals a constant, so you have some nice symmetry in the formula. So if you let alpha beta be pi and replace n by 2n plus 1, then you get this formula for zeta 4n plus 3. So this actually goes back to Lurch earlier in 1901. Well, I've always considered this to be a really remarkable identity because look at what we have here. We have zeta 4n plus 3 is a rational multiple of pi to the 4n plus 3 plus a very rapidly convergent series. So in other words, we can say that zeta 4n plus 3, a rational multiple of pi to the 4n plus 3 for rapidly convergent series, so it's almost a rational multiple of pi to the 4n plus 3. Now, of course, I realize that's not a mathematical statement at all, but anyway, I still enjoy thinking of this as almost the multiple of pi to the 4n plus 3. As most of you know, the arithmetic character of zeta 4n plus 3 is unknown, except for the case when n is equal to 0 here. We know zeta of 3 is irrational, but that's all we know. And here is actually the page of the notebooks where these formulas are found. Well, when I returned to Illinois from the Institute, I, of course, then bought a copy of the notebooks from the Tata Institute. So again, I just took this picture about a month or so ago. You can see that they're now rather worn. So this cost me $25, including shipping. So that's really a great deal. I mean, can you get 3,000 theorems for $25 these days? I don't think so. So that's I think a really good deal that I got here. So as I said, I had these, and when I began in May of 1977, working on chapter 14. I did have this copy. Well, in the fall of 1978, I worked on this for a little over a year. And then George Andrews visited the University of Illinois. In fact, he and his family stayed with us in our home. And one day, during his short visit, he told me that Watson and Wilson's efforts to edit the notebooks were preserved at Trinity College, Cambridge. So I thought, well, if I had a copy of their notes, then maybe I could edit further chapters. So I wrote Trinity College Library for a copy of the notes, and they sent me very kindly all these notes of that Watson and Wilson had accumulated. Yeah. And so then I went back to the beginning and just worked my way through the notebooks. So anyway, that took a little over 20 years before I completed this. So as I was completing this, I approached George Andrews about the lost notebook that he found at Trinity College in 1978. Rankin, by the way, hated that term because he said it wasn't lost. You know, the librarians knew about it and he knew about it, but no one else seemed to know about it. So it was natural for Andrews to call this the lost notebook then. So there are a lot of things in the lost notebook I was really interested in, and Andrews is not particularly interested in, so I said to George, how about writing volumes on the lost notebook like I did for the earlier notebooks? And he said to me, well, I don't know if we can get this in one volume or not. It might take 2 volumes, 2 books to do this. Well, our 5th and last volume on the lost notebook was just published about a month ago. So Andrews is a little bit off in his predictions as to how many volumes it would take us. Okay, so let me just tell you a few things that are also in the notebooks. There are lots of results on Q series, but there are more in the lost notebook than they are in the earlier notebooks. So generally Q series have these products in the summands, but not always. And this is just the infinite version here. So Q is called the base, and if it's unchanged or constant, then we just drop it from the notation and just write A sub n instead of AQ sub n. So there are many, many results on theta functions. And Ramanujan used his own notation for theta functions. He did not use any of the classical notations. So he defined theta functions in this way in a symmetric version. So this includes the classical ones, which are called theta, theta 1, theta 2, etc. And this is a nice version because this is what's called the Jacobi triple product identity. It has a very nice symmetric representation using this representation for the sum function representation of theta functions. So phi of q is just f of q minus q. I gave this representation just because it has a simpler product representation than phi of q. So this is another of Ramanujan's theta functions. These are the triangular numbers. And here are the pentagonal numbers. And this is the pentagonal number theorem here, really. Yeah, or if you're in modular forms, this is essentially the Dedekind eta function. So there are many results on theta functions. So Ramanujan actually never used this notation. He would always just write a few terms of the product, or if he had a sum, a few terms of the sum. In fact, I don't recall that I ever saw any summation sign or product sign in the notebooks. So as I indicated, he didn't use the standard notation for theta functions. He had many, many results on elliptic functions, and again, didn't use any of the standard notations for elliptic functions. So I have the feeling that he actually discovered these for himself without looking at any text. Well, let me say a few words about elliptic functions here. So Ramanujan never gave us the definition, so these are not in his notebooks. So this k between 0 and 1 is called the modulus. This is called the complete elliptic integral of the first kind. And you can represent this as a hypergeometric function, although I really won't use this representation. So here I'm using hypergeometric notation. So here the a sub n has a different meaning than what I showed you previously. And then k prime is the complementary modulus. Okay, so let me define a modular equation. So if you have 4 complete elliptic integrals of the first kind associated with the moduli k, k prime, l, and l prime, suppose you have this relation for some positive integer n between these integrals. Then the modular equation of degree n is the relation between these moduli which is induced by this equality. And then lastly, let me mention that there's a multiplier, which is a quotient of the 2 elliptic integrals, or you can define it as a quotient of the hypergeometric functions. Well, the reason I give all of you this is that Ramanujan loved modular equations, and he has many of them in his notebooks. So I just given 3 here. So for degree 3, I think he actually has 10 or 12 different modular equations of degree 3. And, similarly, for some of the lesser values of n, he has lots of modular equations. So they always, or often have a symmetry to them, so you can see that except for the sign of the terms, the right quality here is the same as the left equality, but with alpha and beta just switched. So these are beautiful equations, and that Ramanujan loved, and they don't duplicate. So in other words, if you look at any of the modular equations of degree 3, none of them will appear for any other degree. So that's true of all the degrees. There's no replication of the modular equations at all. So having said that, let me just tell you about a theorem that was proved about a year ago by my former student, Sun Kim. She established a very beautiful general theta function identity giving products of theta functions. So her goal was actually to prove some conjectures by Ole Varner, an Australian combinatorialist and number theorist, which she did out of her formula. But then she saw that she could actually get some modular equations out of her formula. So she got 3 different modular equations, so they would then be, from what I said, of 3 different degrees. So this is really an amazing formula, because I've never seen anything like this before. A formula which encompassed, as special cases, 3 different modular equations that of 3 different degrees. So really a remarkable result. Okay, so let me just summarize the topics that one can find in the earlier notebooks. So there are lots of identities involving infinite series, and we started off with some of those identities. A lot of work on theta functions, elliptic functions, modular equations. And there are lots of results in hypergeometric functions, many of which are new. And a few things on other special functions, but mostly on hypergeometric series. Okay, basic hypergeometric series are analogs of hypergeometric series, but containing these Q products instead of rising factorials. And as not surprisingly, since Ramanujan is known as a number theorist, there are a number of results in number theory, in particular Diophantine approximation in the notebooks. Okay, so now I want to head to what I've called a final problem. I'll explain those words in a few minutes. And I'll tell you about a couple of results in the lost notebook. Actually, they're not in the lost notebook. They are in a paper published with the lost notebook of just a partial manuscript that Ramanujan had. So this was also, I think, in Watson's attic floor office and sent to Trinity College by Rankin. Well, in Ramanujan's last letter to Hardy, the only letter that he sent to Hardy after he returned to India in 1919, Ramanujan died in April of 1920, he described what he called mock theta functions. So Watson then called his paper here, an account of the mock theta functions, the final problem, because this was the final thing that we know, problems that we have of Ramanujan. And as some of you may know, Watson borrowed this title from Sherlock Holmes. So The Adventures of the Final Problem is probably the most famous of the Sherlock Holmes stories. It was the 24th and last of the Sherlock Holmes. So I got this from Wikipedia, this last paragraph here. It was published originally under, in Strand magazine, under a different title. But Sir Arthur Conan Doyle did not like this title, so after that, it was really known as the, by the Final Problem. In other words, The Adventure of the Final Problem, as Doyle originally meant the title to be then. So this is where Watson borrowed this, and I am borrowing this from Watson as well, as we'll see in just a few minutes. So while I was in London 2 weeks ago, we actually went to the British Library and saw this manuscript, the actual manuscript of the Final Problem. So we couldn't resist taking a picture of this. So you might, I won't read this for you now, but the paragraph written by Sherlock Holmes about Professor James Moriarty is quite interesting. Okay, so before I get to the final problem, I'd like to tell you about the circle problem and then the divisor problem, which is connected with the final problem. So we'll let R2 of n denote the number of representations of the positive integer n as the sum of two squares. So we count different signs in different orders as distinct. So for 5, then there are 8 representations as a sum of two squares, because you could take 2 squared and 1 squared and change the signs in 4 ways, and then you could change the order. And each representation of n as the sum of two squares can be associated with a lattice point in the plane. So for example, 5 is associated with the lattice point. This representation of 5 is associated with minus 2, 1. And then each lattice point can be associated with a unit square. So it doesn't make any difference which of the 4 choices you take. For consistency, we'll take that where the lattice point is in the southwest corner of the square. So if I want to sum all the numbers R2 of n for n less than or equal to x, that's the same then as summing the areas of all of these red squares. So each red square corresponds to a lattice point inside this circle of radius square root x. Okay, so a lot of them lie inside, a lot of them outside, and of course a lot of them around the perimeter. Okay, so we will define then the error term of p of x in this way. This is the sum of all those lattice points inside the circle of radius square root x. So an obvious approximation would be pi times the radius squared, pi x. But obviously that's not going to be exact formula, there's going to be an error involved. And we put a prime on the summation to indicate that if x is an integer, we only count to half R2 of x. You might say that's because, well, if the square lies with the southwest corner on the unit circle, do we count it or not count it or something? So that's one way of thinking of it, but in analyses, using analysis to study this problem, this is the sum that most naturally arises when you apply analytic methods. So finding the correct order of magnitude as x tends to infinity is known as the circle problem. So it's been an unsolved problem for many years. Gauss was the first to look at this problem. So note that all of our lattice points are going to be within a circle of square root x, radius square root x plus square root 2. And then if you take a circle of radius square root x minus square root 2, that'll be all red. So from these two estimates, or bounds, you get that r of x, the summatory function, is pi x plus big O of the square root of x then. So that's the first elementary, the only elementary approach to the error term. So Hardy worked on this problem, the circle problem. And in the paper at the beginning is this relation formula for the summatory function in terms of Bessel functions then. So this is the ordinary Bessel function, J u of z. And then he says that this identity, he says the form of this equation was suggested to me by Mr. S. Ramanujan, to whom I had communicated the analogous formula for the divisor function here. So this actually is due to Voronoi at the beginning of the 20th century. So the proof is not given in the paper, and as far as I know, we don't know Ramanujan's proof, and I don't know Hardy ever knew his proof. But he obviously must have had a proof. You don't get this kind of formula just by guessing that. Well, also in the paper is this beautiful identity of Ramanujan that Hardy gives, and it's not given anywhere in Ramanujan's work. So if we didn't have this paper of Hardy, we would never get this formula, which leads to the question, how much else of Ramanujan's work has been lost and we never have discovered it. Well, this is a beautiful formula. You get from the left side to the right side by just interchanging the A and the B. So you have to admit, this is a beautiful formula. If you don't think this is a beautiful formula, you're not a mathematician. Every mathematician has to agree this is a beautiful formula. Well, if we differentiate this with respect to B, let A tend to 0, replace 2 pi square root B by S, use analytic continuation, we get this formula here. And this is actually what Hardy used to study the circle problem. Now, he had his own proof of this formula in his paper. So he didn't actually give this argument that I just gave you. Okay, so this is a key in Hardy's proof that the error term is omega plus or minus x to the 1/4. So let me explain this notation. So for the plus sign, this means there's some sequence of xn's tending to infinity such that the error term is bigger than some positive constant times xn to the 1/4. And there's another sequence tending to infinity such that the error term is less than minus a constant times xn prime to the 1/4. So this means that the error term, you actually only need one of these to conclude this, is at least x to the 1/4. So most mathematicians think that this is the closest that we have. In other words, the error term is close to x to the 1/4, the order, but we never have proved this. Okay, I want to tell you about another identity connected with the circle problem that's in this unpublished paper of Ramanujan. So if you teach a course in elementary number theory, you might get this representation for R2 of n. This is due to Jacobi. So you can prove this using elementary number theory. Okay, I'd like to rephrase this and use it in the summatory function. Okay, so I'm going to write minus 1 to the d minus 1 over 2 in terms of a sign. And then I realize that for every divisor n, there's of course another divisor j, such that dj is equal to n. So I consider this then as a sum over all pairs dj where the product is less than or equal to x. But then I sum on j now first, and the sum on j, I think you can see, is just the square brackets of x over d, whereas the square brackets is the greatest integer function or the floor function. Okay, so keep this in mind when I give you Ramanujan's formula. So he states it, and I'm using his notation, f of x is the square brackets of x if x is not an integer, and again reflecting the prime notation, x minus a half if x is an integer. Okay, so this is Ramanujan's formula for this unpublished manuscript. So this is printed a few years ago by Sun Kim, who I mentioned earlier, and myself and my colleague Alexandru Zarescu. So it's an amalgam of two formulas. So here we have on the left-hand side the square brackets function, essentially. And instead of having the simple sign function that we had, we have a more complicated one involving an extra parameter, theta. And then on the right-hand side, we have a double series of Bessel functions as opposed to a single series that we have in the formula that he gave to Hardy at the beginning of this paper. So it's sort of an amalgam of an elementary formula and the other formula that Ramanujan found. So in analytic number theory, if you can introduce another parameter into your analysis, that gives you something more to work with. And so I think that, but I don't know, of course, that Ramanujan introduced this extra parameter theta in order to try, he had some ideas for working on the circle problem, but I don't know. This is all we have. So this is just the reference of our paper where we finally proved this formula. So again, note that the left side is finite, discontinuous if x is an integer, and we have these singularities at theta equals 0 and 1, as you can see from the cotangent function appearing here. And if this is true, the singularities are actually canceling each other out, because as a function of theta, the left side is analytic. So somehow these Bessel function series cancel out the singularities that you get from the cotangent. Okay, well, Zarescu and I first proved this result with the order of summation reversed. And that is a little bit easier. So it took us a while then. Of course, Sun Kim came along and helped us here before we found a proof with the way Ramanujan actually stated the formula. So the two proofs are entirely different. Okay, so yeah, this is what I just mentioned, that the summands have a resemblance to those in the original identity. So you might ask if we can get one from the other, and actually we can. But not as an iterated summation, but with the product of the indices m and n tending to infinity together. So this is then a third way of looking at the summation. So Ramanujan might have used this idea, but I really don't know. So three different formulations, with Ramanujan's formulation being the hardest to prove with them. Okay, now let me get to the Dirichlet divisor problem. So this is to estimate the sum of d of n, the number of divisors of n. And this is elementary, but it's much more difficult than the argument that I gave for the circle problem. And this is the error term. Yeah. And you can show by elementary means that the error term is big O square root of x. So the Dirichlet divisor problem asks for the correct order of delta of x as x tends to infinity. And just as with the circle problem, you can associate every divisor d with a lattice point. So here, the lattice point would be dj, where j is n over d. So finding then the sum of d of n less than or equal to x, is equivalent to finding the number of lattice points under or on this hyperbola yz equals x. Okay, and this is what I just mentioned. So there's another elementary representation here in terms of the square brackets function. So again, just d of x is the, I think my light just went out, sum of just lattice points, or the sum of 1. And then we can sum on j first, and then you get square brackets of x over d. Okay, so let me give you an analog then of Ramanujan's identity for the R2 of n as a double series. So here we get these differences of ordinary Bessel functions coming into play. Yeah, sorry, I guess my light has gone out. And so these two Bessel functions then arise in the next identity. So here is the identity for one series. So this really goes back to Voronoi. So let me state then Ramanujan's identity in terms of the same function f of x that we used before. So now again, we have a double series of Bessel functions. And instead of a sine, we have a cosine on the left side. So in view of the elementary formula, and in view of the formula in terms of Bessel functions, again, this is sort of an amalgam of both formulas. And my guess is that Ramanujan introduced theta here, and he had some ideas as to how to prove, get a result on the error term for the Dirichlet divisor problem. But we don't know anything more. Okay, well this turned out to be very difficult to prove. So in our paper with Sun Kim and Alexander Zarescu, we had proved the formula with the order of summation reversed. But we had to assume convergence at one value of theta. So if we had convergence at one value, then we got it for all values of theta between 0 and 1. But this is with the order of summation reversed from what we have in Ramanujan's statement. And we can also prove the identity if we let the product of the indices tend to infinity. Okay, well, the last problem that we really faced then was to really prove Ramanujan's formula as he stated it. So in the last book that Andrews and I wrote on the Lost Notebook, we did not have this proof. So this is the final problem. And Zarescu suggested it to one of his students, Junxian Li, last spring. And then, in fact, we eventually then solved the final problem and have a proof of the identity as Ramanujan put it in his unfinished paper then. So this is the final problem, the proof of this identity. So this is my co-author, Alexander Zarescu, and Junxian Li, our graduate student who's now in Germany. She got her PhD this past spring. So my life with Ramanujan will continue, and thank you very much for inviting me to talk about Ramanujan.
So are there any questions for our speaker?
If you've solved all the problems, what's next?
Trying to figure out what Ramanujan thought for these problems. Thank you, Larry.
Does this give you any new insight on the circle problem? These new results?
No, I was hoping it would. I was hoping that, I could figure out, why Ramanujan introduced this extra parameter theta. I can't really get back to the summatory function. So, yeah, I don't know what to do. I've thought about this a lot.